So, Zahib, Hania, can you hear me?
Yes, sir.
So we're going to start with this question. We're going to start with this organic question. I have somewhere. I have the organic revision chart, and so now we're going to start with this question over here. The question states that. So the question states that each of the three organic compounds BWX have the empirical formula CH2O. So that's the empirical formula. They have the same. They've got the same empirical formula, and you're given that V gives the brick red precipitate when warmed with Felling's reagent. So the first thing is, what is V, and what happens when Felling reagent is reacted with it? So this thing is, Felling is over here. Aldehydes, they get oxidized. Oxidation happens with the aldehydes, and they turn into carboxylic acid. This happens when you react it with a Felling reagent. You get a brick red precipitate. So V must be an aldehyde. That's the first thing. So the first one we figured out that V is an aldehyde. What about the second one? W and X do not. So that kind of indicates that. So that kind of indicates that is W and X are not aldehyde. So V is an aldehyde. I'm just going to write it in front of that. And these two are not aldehydes. So that's the first information that you're getting. W is a fruity smell. So, I mean, that clearly indicates that it's an ester. So we figured out that W over here is going to be an ester. So that's our ester. And in X, so the last one in X, and they've given you the number of carbon atoms. So that is also going to make it easy. Now in X, the carbon atoms are bonded directly to one another. So find the carbon atoms. So that indicates the 3 carbon atoms are bonded directly to one another. That's what this information states, that the carbon atoms are bonded directly to one another. And X gives an effervescence when shaken with sodium carbonate. V and W do not. So X is clearly a carboxylic acid. So it must be a carboxylic acid, because only carboxylic acids, they react with carbonates. So that is what you're going to get. That is the information that you're going to get from this. So give the structural formula of V. So 1 carbon atom aldehyde, that's what V is. So just 1 carbon atom aldehyde. So that's it. So what functional group is present in W? So W is an ester. So that's so if we figure that one out, give the structural formula of W. So you need to make a 2 carbon atom ester. That is what you got to do. So an ester has double bond O, and O, it's a 2 carbon atom ester. So there's going to be another carbon over here. This will have 3 H's, and this will have 1 H only. And the last one is when X is heated with about X, remember the empirical formula is this. It's CH2O. So if you have C3, then according to the empirical formula, the H would be 6 and O would be 3. So that kind of indicates that that the only possible way you can have a 3 carbon atom carboxylic acid is you need to include another oxidant to this. So this molecule could be, there might be an OH as well. So it might be a carboxylic acid with an OH group, because you need 3 oxidants. And this makes it C3H6 and O3. So that's C3H6O3. And so there must be an OH group and alcohol group as well. But there are 2 options now. The OH group could be on the the last carbon atom from the right, or it could be on the middle carbon atom. So this X will have, you'll have two different molecules that could be X. One of them could be that it could be that the OH group might be in the middle somewhere. So that's another option. So one of them is a primary alcohol. This one is a primary alcohol. And this one over here is a secondary alcohol. So anyways, I'm going to talk about X a little bit. So these two are your options for X. He said about X that the carbon atoms were bonded directly to one another. So all the 3 carbon atoms were bonded directly to one another. The other information that was given was that it was reacting with sodium carbonate. So that meant it was a carboxylic acid. So I added a carboxylic acid to it. So it was a carboxylic acid. It could be, I mean, this one could be a carboxylic acid. So, and when I looked at the empirical formula which they had given us before, that was CH2O. The empirical formula came out to be like, if you have 3 carbon atoms, the empirical formula is C3H6O3. So from that, I figured out that apart from a carboxylic acid, there must be another O, and that's going to be an OH, because only then will you have 6 hydrogens. So there would be a third oxygen, which would be an OH oxygen. And so that's, I mean, you've got these 2 options. Now he's saying that when X is heated under reflux with K2Cr27, the product Y gives no reaction with 2,4-DNPH. Now, what is 2,4-DNPH? 2,4-DNPH is this thing. 2,4-DNPH is over here. Carbonyl compounds, aldehydes, and ketones, they give a positive result with 2,4-DNPH. So that means that once oxidation happens for this molecule, you're not getting a carbonyl compound. So which means that the alcohol must be, I mean, the alcohol must have been a primary alcohol, because it's turning into a carboxylic acid. Primary alcohols, they get oxidized to aldehydes, and aldehydes get further oxidized to carboxylic acid. So it must be an oxidation reaction that goes all the way to carboxylic acid. It might not be a secondary alcohol, because if it was a secondary alcohol, secondary alcohols, they turn into ketones. Ketones are carbonyl compounds, and they do give orange precipitate with 2,4-DNPH. So it's not a secondary alcohol, it's instead a primary alcohol, and the oxidation is not stopping at aldehydes, it's actually going all the way till carboxylic acids. So must be a primary alcohol, which means that I've figured out the molecule. It's going to be this one. This is what X is. Not this one. This is not X, because it's a secondary alcohols. And if you oxidize a secondary alcohol with K2Cr2O7, you get a ketone. And a ketone will give a positive result with 2,4-DNPH. So give the structural formula of X. So write the condensed formula. It's OH on one side, followed by CH2, then another CH2, and then there is COOH. So this here is X. And give the structural formula of Y, the compound formed from X when oxidation happens. So the alcohol also turns into, I mean, this side was already carboxylic acid. The primary alcohol over here will also turn into carboxylic acid. And the middle one would be 2 hydrogens. I said then when X is formed with a little concentrated sulfuric acid, a small amount of cyclic compound Z is formed. Z has the molecular formula of this. Find out what this is. So this is, what carboxylic acid is. I mean, this is what X was. Now the X was an alcohol as well as a carboxylic acid. Now we know that carboxylic acids and alcohols, they react together to form esters. So the same molecule, remember there are 3 carbon atoms, Z has 6 carbon atoms. So the same molecule kind of reacts with itself. There would be another version of the same molecule. It's going to have 3 carbon atoms, and there's going to be OH over here, and there's going to be OH and double bond O, carboxylic acid on this side. And there would be 2 hydrogens here and 2 hydrogens on this carbon atom. What will happen is that the OH is lost and the H is lost. And an ester link would be formed between them. So an ester link gets formed between them. Remember, this was an alcohol, this was a carboxylic acid, the OH is lost, the H is lost, a water molecule is formed. The same thing happens over here. The carboxylic acid OH is lost, the H is lost. And they're going to end up forming an ester link as well at this point. So it would be serial bond O, and that's how the ester link would be formed. Okay, Zahib, Hani, is this clear? And that's your displayed formula. When you talk about the displayed formula, you show all the atoms and all the bonds. And it's a condensation reaction. So just remember, whenever esters are formed, you got a carboxylic acid and you got an alcohol. The OH is lost, the H is lost, and water gets removed. And the serial bond O links up with the oxygen from the other group. The same thing was happening here as well. I'm just going to show this again, that you had an OH and you had a carboxylic acid OH. The carboxylic acid loses its OH, it loses its H, and the two end up linking together. So there was a carbon here. And that's how the ester was formed at this point. Then the next one is you're given 6 molecules, and what is the empirical formula of compound T? So this is T. You just have to figure out what the actual formula is. Like how many carbons it's got. It's got 1, 2, 3, and 4 carbon atoms. So that's C4. You can count the hydrogens. That's 1 plus 2, that's 3, 4, 5, 6, 7, and 3, 10. So that's 10 hydrogens. And how many oxygens? You got 1 over here and 1 over here. So that's 2 oxygens. You can simplify this. This would be C2, H5, and I think O would be 1. So that's your empirical formula. And draw the skeletal formula of S. So S is how many carbons? That's 1, 2, 3, 4, 5. So skeletal formula 1, 2, 3, 4, and 5. And on the 5th carbon, there's an OH. So remember all these points on the chain: 1 carbon, 2 carbon, 3 carbon, 4 carbon, and 5 carbon. Those are your 5 carbons, and there's an OH that's attached on the last one. Now, compound S and U are isomers. So what are S and U? Look at S, look at U. The type of isomers is, there are 2 types of isomers mainly. There are structural isomers, and then there are structural isomers. I mean, this one is structural isomers. Why? Because the structure is different. You got an OH group here, and there is no OH group here. So compounds S and U are structural isomers of each other. They're structural isomers of each other. The other type of isomerism is stereoisomers, where the molecular formula is exactly the same, except that the bond orientation is different, like optical isomers, where you have chiral carbon atoms, mirror images, or you have cis and trans. Now, 2 of the 6 formula P to U can each be drawn in 2 forms, which are known as stereoisomers. Which 2 compounds have formulas that can be drawn in 2 forms? So the first thing you're going to look for is the mirror images, the optical isomers. For that, you're going to look for a chiral carbon atom. A chiral carbon atom is a tetrahedral sp3 hybridized carbon atom, where it's bonded to 4 different groups, and it forms 2 mirror images. Just like your 2 hands, the molecule will exist in 2 forms, which would be mirrored versions of each other. They look the same, but not exactly the same. So we're going to try and look for a chiral carbon atom. Which molecule is going to have optical isomers? That's the first one. So for this, we have to find this chiral carbon atom. So look carefully and you'll spot somewhere a chiral carbon atom, 4 different groups. So I think it's probably D. D over here is specifically this carbon over here. I'm going to draw this carbon. It's CHOH with a CH3. Just 1 second. I'm going to draw it over here. So it was CH with an OH with a CH3. I mean, 3 sides are different. So let's go back and have a look. Focus on this carbon atom, C with an H and an OH as a branch. And you've also got a CH3. And on the other side, it's CH2, CH2OH. So on the other side, you've got a CH2, another CH2, and an OH. So this carbon is chiral. It is bonded to 4 different groups. And it's going to have another version of it, and it's going to be a mirrored version of the same molecule. There's going to be a mirrored version of this. So this one is chiral. And so that's the first one, that's D. And the type of isomerism would be optical. The other type of isomerism that you can look for is the geometric isomers, where the conditions for a geometric isomer is that there has to be a double bond, and the 2 groups that are attached to the carbon in the double bond must be different. For example, this is one example. So there would be 2 versions of this molecule where the direction of the bonds would be different. They would be bonded to the same atom, except that the direction of the bond would be different. Like the H is pointing upwards, the Cl is pointing downwards. Over here, the H would be pointing downwards and the Cl would be pointing upwards. So the only difference between the 2 is that the 3-dimensional shape of the molecule is different. They have the same structural formula. The H is still bonded to the same carbon atom, except that it's pointing downwards instead of pointing upwards. In geometric isomers, you've got a cis and you've got a trans. Cis is when the same type of groups are pointing in usually it's the hydrogens that are pointing in the same direction. Trans is when the same type of groups are pointing in opposite directions. So I'm going to look for a double bond. So who's going to make cis and trans? It's going to be this one. Remember, the carbon atom in the double bond must be bonded to 2 different groups. Over here, the carbon is bonded to 2 hydrogens. So it's definitely not going to form cis trans. It's going to be this one. And I can draw the 2 versions of this. There's going to be a double bond. Around the double bond, the molecule is fan-shaped. So that's your double bond. This carbon over here is bonded to an H and a CH3. The carbon on the other side, that's bonded to an H and a CH2, CH3. So there's going to be this is the cis version of the molecule. And there's going to be a trans version of the molecule where same stuff, everything would be the same, H and CH3. Except the H with this carbon atom would be pointing downwards and the CH2, CH3 would be pointing upwards. So that's your trans version because the H atoms are pointing in opposite. They're pointing in opposite directions. So this molecule P is going to form geometric isomers. So remember this, that there would be 2 types of isomerism. There's going to be optical and there's going to be geometric. There are 2 types of stereoisomers. Then you're coming to reactions. Compound X can be converted into compound R. What type of reaction is this? So S to R. So you got an alcohol, it's turning back into an alkene. So look at the chart. What happens? You've got an alcohol. It's called dehydration or elimination. You got an alcohol, it turns back into an alkene. What happens is that the OH is lost. And like if I go back, what's going to happen is the alcohol OH would be lost and the H from the neighboring carbon atom would be lost and they would turn into a double bond. So that is what will happen. It's going to be a dehydration reaction. So you can call it a dehydration, or just to be on the safe side, elimination, because a water molecule gets eliminated. What type of reagent would you use? You can use Al2O3. I mean, this is given over here. Dehydration is Al2O3 plus heat, or concentrated H2SO4 as well. Both are dehydrating agents. The next one is write the structural formula of the compound formed when T undergoes the same reaction using excess of the reagent you have used in C2. Write the structural formula of the compound formed when T undergoes T. What is T? I think it's the same reaction. T is also an alcohol. It's got two OH groups. So it's 1, 2, 3, and 4 carbon atoms. There's an OH on the third one and the first one. So let's try and figure out what's going to happen if we do the same thing with T. So it's got 1, 2, 3, and 4 carbon atoms. There's an OH on the third one, and there's an OH on the first one. And you've got H and another H and another H and another H. Chalo yoga. The OH is lost and the H is lost. The OH is lost and the H is lost from the neighboring carbon atom. So a double bond would form over here and a double bond would form over here. So they're going to be two double bonds that are going to be formed. Same reaction, dehydration with T, that would result in a diene, a molecule with two alkene groups. So because it had two OH groups, that resulted in two double bonds. Next is
Sir,
Haji.
Is there a possibility that in the structure you're drawn above, that double bond forms in the middle?
Okay, OH is lost. The problem is it is a possibility, but not likely, because if the OH is lost here and the H is lost here, the double bond would be formed over here. Usually two double bonds cannot be right next to each other. That would be, I mean, it is a possibility, but the safe bet is this one. It would form, the OH would be lost and the H would be lost from the other side. Okay, is this clear?
Yes, sir. Thank you.
As the next is, what is the structural formula of the intermediate compound formed in this sequence? So the intermediate, I mean, you've got a sequence here, and you got an alkene and it's turning into a ketone. So it's probably a ketone. I mean, look at the chart. How can you turn an alkene into a ketone? So you have to take this route. You got an alkene, you turn it into an alcohol, and that alcohol can be oxidized to a ketone. So that's the only path that you got. Alkene, hydrate it, add water to it. There are two ways of making an alcohol. You can either turn it into a diol, like cold alkaline KMNO4, and it will form a diol. Or you can add water to it, then it would form a simple alcohol, and then that could be oxidized to a ketone. That's what's going to happen. So we're not going to make it into a diol because there's only one ketone group over here. So must be just one water molecule getting added. So it's going to be CH3, and then there's CH. You had a double bond. Then you got CH2 and CH3. So so what would have happened was there must have been an H added and an OH added. And that double bond would turn into a single bond. So it must be an alcohol, and this alcohol, so that's hydration. And then this secondary alcohol would get oxidized to a ketone. So outline how step 1 may be carried out to give this intermediate compound. So I think all you have to do is hydrate it. So that's you add water to it in the form of steam, because the temperature is really high, 300 degrees centigrade, and it's 60 atmosphere pressure. And phosphoric acid is used as a catalyst in the reaction. Or it could be any catalyst. Sulfuric acid is avoided because it's a good oxidizing agent as well. So that's the reaction. That's you got phosphoric acid, 360 atmosphere. That's going to make it into an alcohol. Okay, what reagent would be used for step number 2? That's oxidation. You have to turn the alcohol into a ketone. So KMNO4 or K2CR2, so preferably K2CR207. acidified, and reflux. They're just asking. So they're just asking for the reagent, acidified and reflux. I'll write the conditions as well in this case. As a next one, I'll skip the moles question, just doing organic. So, I mean, let's try and do this one. So the astronomers using modern telescopes of various types have found many molecules in the dust clouds in space. Many of these molecules are those of organic compounds, and astronomers constantly looking for evidence that amino acids, such as amino ethanoic acid, are present. So this is the basic building block of living organisms. One molecule that has been found in the dust cloud is hydroxyethanol, and it contains two functional groups. So hydroxyethanol is it's an alcohol and an aldehyde. So that's the answer to the first one. And you can be very specific that this one is a primary alcohol. So you can be kind of specific about this. So it's an alcohol and an aldehyde. And for each functional group, identify a reagent that will react with this group and not react with the other group. In each case, describe, so functional group number 1, what will react with aldehydes? 2,4-D and pH. Like, look at the chart. Aldehydes, they give an orange precipitate with 2,4-D and pH. Alcohols don't. So this is a very specific test for aldehydes and ketones as well. But you've got an aldehyde. So we need to identify a reagent. I'm going to identify 2,4-D and pH. And the observation is going to be, you're going to get an orange precipitate. That's a test for identification of aldehyde groups. Functional group number 2, you want a reagent that will only react with alcohols. So find something that only reacts with alcohols. Now, the common thing about them is alcohols and aldehydes, they get oxidized. So the other thing, the other reagents that you could have used was apart from 2,4-D and pH, you could have talked about toluenes or phelings as well, because they're also very specific to aldehydes. They oxidize aldehydes, but they're very specific to aldehydes. But anyways, you're looking for a reagent that will only react with alcohols. You could talk about sodium metal, because that will only react with alcohols. It's going to be a very slow reaction. And there are lots of other reagents, like you can dehydrate. So the kind of other reagent, let's go with sodium. That should be good enough. So we can go with sodium. And the observation would be, you will see effervescence, so bubbles of H2 gas that are going to be formed in this case. Now, and remember, it's an alcohol. Okay, somebody is saying sodium carbonate, so that's definitely not correct, because sodium carbonate is for carboxylic acids. I mean, alcohols, they only have one acid type reaction, and that is with very reactive sodium metal. So then you've got, give the skilled formula of the organic compound formed when it's reacted with the following NaBH4. That's reduction. What will happen is that the aldehyde with NaBH4 is going to get reduced back to an alcohol. This part, it's this part. So that's what you're going to do. Turn this back into an alcohol. So it's going to become a diol. It's I mean, this part was already an alcohol. The other part, which was the aldehyde part, would also turn into an alcohol. So it's going to turn into a diol. The other part is now you're oxidizing it. When you oxidize it, remember, aldehydes get oxidized as well as primary alcohols. They both get oxidized, and they kind of turn into the same thing. Look at the chart. Primary alcohols, they turn into aldehydes, which then get further oxidized to carboxylic acid. Same thing happens with aldehydes, they turn into carboxylic acid. So you're going to get both the carbon atoms turning into carboxylic acid. So that's what you're going to get in this case. This side would turn into carboxylic acid, and the other side would also turn into a carboxylic acid. So both of them are going to give you carboxylic acids. In a school or college laboratory, Zaib, clear है ये पिछला?
Yes, sir.
अच्छा, अब ये कि school or college laboratory, there's a process given. So by considering the possible reactions of the following groups, you basically have to identify, I think, X and Y. They didn't give you anything else. So this thing is easy. Now you want to turn an aldehyde into a carboxylic acid. That's kind of easy, not that much of an issue. Aldehyde into a carboxylic acid, you got lots of reagents, oxidize it. K2Cr2O7 is fine enough. So you just need to oxidize that. So that part is easy. How do you turn an OH into an NH2? I mean, the right side, I don't have an issue with that. I can turn the aldehyde into a carboxylic acid at any point. Just oxidize it. But how do I turn an alcohol into an amine? For that, I would have to do a couple of things. What I would have to do is, I would have to first turn the alcohol into a halogenoalkane. Like I can react it with PCl3 plus heat and turn it into an halogenoalkane. And then I can do nucleophilic substitution. So this path, an alcohol, I'll turn it into a halogenoalkane by reacting it with PCl3. So the OH in the alcohol gets substituted by a halogen, and then I can do nucleophilic substitution with ammonia, and it will turn into an amine. So this is what I'm going to do. So X would be, so let's turn it into X. It would be CH2, CHO, and over here, instead of the OH, I'm going to have Cl. And I'll use PCl3 plus heat. I'm going to react it with this. Now, the other one is, so I got this. Now the next part is I'm going to turn it into, replace the Cl with ammonia. So that would be ammonia ethanolic. And reflux, or ammonia gas in a sealed tube at high pressures. I'm going to heat it. So the CH2, this side is the aldehyde. I'm not touching the aldehyde side, and this side becomes an H2. So I got the amine. And the last part is I'm going to oxidize it. Remember, I'm going to oxidize it at the end, because if I had oxidized it at the beginning, then the trouble would be that the alcohol would be gone because it would turn into a carboxylic acid. I don't want to do that. I want to turn it into an amine. So I want to keep the alcohol. I want to keep it, turn it into a Cl, turn it into an NH2. So at the very end, I'm going to oxidize the aldehyde. So this would be K2Cr2O7. And it will be acidified and reflux. So the reagent and conditions are given. Now the next one is state the reagents for each of the three steps you have chosen. Step one, so I've done that. So let's skip that. Let's move to this one. This one is kind of an easy question. We can try and do this one. First thing, strong oxidation. Remember, hot concentrated KMnO4. So that's strong oxidation. Now, whenever you have strong oxidation, what will happen? The double bond over here, it's going to break. And this is the oxidation of alkenes. So the double bond breaks. And when the double bond breaks, you got three different scenarios. Scenario number one, you got a double bond with two carbon chains that gets converted into a ketone. You got a double bonded carbon atom with one carbon chain and one H that gets converted into a carboxylic acid. And you got a double bonded carbon atom with two hydrogen atoms that gets converted into carbon dioxide and H2O. So we just need to break the double bond first, and then we have to figure that out. So the first thing is I'm going to get rid of the double bond. Here's the molecule. It's CH3, CH2. Then this was CH. And then I had the double bond, and then the other carbon atom had two H's. So the double bond is going to break in the middle. This side, whenever you have a carbon with two H atoms, the chart tells us that it turns into carbon dioxide and H2O. So one of the molecules would be carbon dioxide and water. That's what you're going to get from this. And whenever you have a carbon atom with one carbon chain and one H on one side, that thing will turn into a carboxylic acid. That particular carbon atom, focus on that carbon atom. If you got a carbon chain and an H, that carbon atom would turn into a carboxylic acid. So we're going to make this into a carboxylic acid. It would be CH3, CH2. And that particular carbon atom will turn into a carboxylic acid. So that's your product of oxidation. And you just wanted to write the organic compound. You can write both of them just to be on the safe side. Then cold dilute KMnO4. When you have cold dilute KMnO4, nothing happens. The double bond simply turns into a single bond and OH groups get added to it. So this time it's going to become CH3, CH2. You had a double bond C. So OH groups, 2 of them are going to get added. 2 of them are going to get added to it. And then you've got water with the catalyst. So that's a hydration reaction. So 2 products are going to be formed. One would be major, one would be minor. So water, H and OH are going to get added. H likes to get added to the carbon that's already bonded to more H atoms. So it's going to be CH3. And then you've got CH2. You got a double bond in the middle that will go away. An H will get added and an OH will get added to these 2 carbon atoms. And the double bond in the middle would go away. So you'll have an H and OH. And this is going to be your major product. Over here, you have your major and minor issue. One of them is a major product. The H likes to bond with the carbon that's already bonded to more H atoms, according to Markovnikov's rule. Now, so the Markovnikov's rule states that the H likes to get bonded to the carbon that's already bonded to more H atoms. So remember this, and the reason for that, I mean, you should know the reason for that as well. And the reason for that is, for Markovnikov's rule, is this one. Whenever you have an unsymmetric alkene, remember, during the electrophilic addition reaction, whenever you have an unsymmetric alkene, during the electrophilic addition reaction, the H has 2 choices. It can steal electrons from the double bond and bond with the carbon on the right, or this H can steal electrons from the double bond and bond with the carbon on the left. So whichever carbon it bonds to, the other one becomes a carbocation because the H stole electrons from the double bond. So this carbon is electron deficient now because the double bonded electrons are with the H atoms. H stole those electrons, this H over here. So the thing is that a carbocation that has more carbon chains is more stable. I mean, this one is more stable. If the carbocation is right in the middle of the chain, if the carbocation is right at the end, it's not that stable. And the reason is that this particular carbocation, the positive charge is going to be very strong. And the reason for that is, why is the positive charge so strong? Because it's not surrounded by large groups. It's got 2 hydrogen atoms. Hydrogens don't have a lot of electrons. They just have 1 electron. So the positive charge is not surrounded by large groups. So which is why the positive charge is really strong. Over here, what happens is that the positive charge is kind of weak. It's weak because it's got 9 electrons over here on the right side. It's got a group attached over here. There's 9 electrons over here. So it's surrounded by electrons. So the positive charge in its neighborhood on both sides, it's got lots of electrons. So the positive charge kind of gets neutralized by those electrons. So, and the reason is carbocation, which has more electron donating alkyl chains, like if it has more alkyl groups around it, it's going to decrease its charge density, and the carbocation would become more stable. So the charge density would be lesser. Over here, the positive charge would be so strong that it will not allow the H to take away the electrons in the first place. So this carbocation would be very difficult to actually form because the positive charge is so strong, because the H was the one that was stealing electrons from it. It will not allow the H to steal electrons from it. So this carbocation is very hard to form. So the H kind of likes, it's a lot easier for the H to bond with this carbon atom because the positive charge that's formed over here would be weaker. So it will allow the H to steal electrons, and the H will be able to get away with it because the positive over here would not be strong enough to pull those electrons back. So you have to remember this. They're going to ask you for the explanation for this. Make sure you know this. So next is, so remember Markovnikov's rule. The H always likes to bond, and remember the reason for that. Remember that secondary carbocations or tertiary carbocations are more stable, and they've got lower charge density because they're surrounded by more alkyl chains. So the carbocation is a lot more stable. Anyways, you could need to oxidize this. So you got a secondary alcohol, you got a primary alcohol. So let's oxidize it. Secondary alcohols, they turn into ketones. And primary alcohols, they turn into carboxylic acids. So that's going to be your reason. So just a second, I'll explain this part. Okay, I'll explain this part in a bit more detail. Remember they're going to ask you specifically now. They're going to ask you. In older past papers, they don't ask you about the reason for this. Why does the H bond with the carbon that's already bonded to more chains? But remember now they're going to specifically ask you the reasons for this, about Markovnikov's rule. So the thing is that when this reaction was happening, this reaction had a particular mechanism. And that mechanism was electrophilic addition. Like you had an H, a water molecule that was reacting with it. So you had H and OH. The positive H was actually getting attracted to the double bonded electrons over here. Okay, let's ignore this. Just let's focus on the first part. Why does the water molecule get attracted to it? So I'm just simplifying this. The positive H is the one that's going to get attracted to these electrons over here. And there would be two carbocations that are possible. So you had a double bond, NH, NH. And let's say the positive H bonds with the carbon over here. The positive H comes. It steals the electrons in the double bond, so that turns into a single bond, takes away those electrons, becomes positive, and the carbon will become positive now because the H took away electrons from the double bond. So the thing is that this positive charge over here is so strong. Why is it strong? Because it's not surrounded by electrons. There's only one electron over here. There's only one electron over here. So it's not really surrounded by electrons. So that means it's not going to get neutralized. I mean, it's not going to be able to, because the neighborhood doesn't really have a lot of electrons around it. So that means the positive charge is really strong. If the positive charge is really strong, it would be very difficult for the H to actually take away the double bond electrons from it, because the carbon will be pulling those electrons very strongly. Which is why this carbocation would be very unstable. When you have a very strong positive carbocation with a very high charge density, it would be very hard for this H. I mean, this was the H that was coming to steal those electrons in the double bond. It would be very hard for that H to steal those electrons because the carbocation formed would have a really strong positive charge, and it will pull those electrons back. It would allow it to take those electrons away. On the other hand, if you have this other carbocation forming, so on the other hand, if you have this other carbocation forming, there's an H positive coming in. It comes in, takes away electrons from the double bond, pulls those electrons towards itself, neutralizes its own positive charge. This carbocation is formed because the H came in and took away electrons from the double bond. Now, what will happen is that the positive charge is going to be weak. It's not going to be that strong. Why is it going to be weak? Because this carbon has a lot of electrons around it. It's got a carbon chain over here. There are lots of electrons on the left side. There are lots of electrons. There's another carbon on this side. There's 6 electrons over here. There's a carbon on this side. There's 6 electrons over here. So this carbon is surrounded by electrons. So its positive charge would kind of get neutralized, because if a positive charge is surrounded by electrons, the positive charge kind of gets neutralized. So it's going to be weaker. So the H will be able to pull electrons away from the double bond and bond with this carbon atom. It would be easier for the H to do that. So it would be easy for the H to steal those electrons. So the carbocation is considered to be a very stable carbocation because it allows the H to take away electrons. It would be a lot difficult if the H was bonded to this carbon atom because the positive charge over here formed would be very strong, and it will not allow the H to take away electrons from it in the first place. So just remember that all you have to do is, you don't have to go into a lot of detail about this. All you have to know is this thing, that why does H, I mean, this is the only thing you should know, that why does H bond with the carbon that's already bonded to more H atoms? Because the carbocation that is formed has more alkyl chains. The positive charge is right in the middle of the chain. So carbocation has more electron-donating alkyl chains around it, which decrease the charge density and which makes it stable. This positive one is very unstable. Now the next one is compound T reacts with U. Draw the displayed formula of the organic product of this reaction. So T reacts with U. T, where's T? T is an alcohol, use a carboxylic acid. So T is a secondary alcohol. It's a butanol. So it's butanol, and I say again, I just started seeing the chart. Just a second. So it's a secondary alcohol, and this one is a carboxylic acid. So a propanoic acid to be specific. So secondary alcohol and propanoic acid, that's an ester. So propanoic acid and a secondary alcohol. Remember, you have to kind of bring the OH groups in front of each other. So I'm going to, so the OH is lost and the H is lost, and they're going to form an ester link in the middle. So the carboxylic acid, and they would form an ester link in the middle, and you can add in all the hydrogens. There would be 3 hydrogens with this, 1 with this, 2 with this one, 3 with this one, 2 with this one, and there would be 3 over here as well. Now the next one is, forget moles, just a second. You're just trying to find it. So let's try and do the previous question. So I've got a I think we did this astronomer thing, but let's try and do this question again. Now, now you got astronomers using modern spectroscopic techniques of various types have found evidence of many molecule ions and free radicals in the dust cloud in space. ठीक है, मैं actually एक सेकंड मैं आंसर कर लूं. ठीक है, I'll probably have an A2 organic class tomorrow as well. Achha, now this one. You have to figure out the shape of a Dorian cross diagram of C2 and suggest the shape of the molecule. So I mean, you can kind of he's saying dicarbon can be produced in laboratory, and analysis of it shows that the sequence of atoms in this molecule is, so you got a carbon. He said that it's carbon oxygen. So carbon with another oxygen, and there is no unpaired electrons, but one of the atoms is only surrounded by 6 electrons. So remember, no unpaired electrons. Now carbon makes double bonds. It's going to form a double bond here with oxygen. It's going to form a double bond here with this carbon. Oxygen will have 4 electrons left, and carbon has 4 electrons. 2 of them get bonded over here, so there would be 2 electrons. And let me shade that. They're going to be 2 electrons left with this one. Now, so the organic revision chart now just message me, send me a WhatsApp. I'll just send it TK after class. I'll just post it TK. I said this one, you have to figure out the shape of the molecule. That's going to be linear. And it's going to be 180 degrees. That's the bond angle because it's just a double bond, one double bond here and one double bond here. He already said that there are no unpaired electrons, but one of them was surrounded by 6 electrons. So this one is surrounded by 6 electrons. फिर अगला है कि what is meant by the term free radical? So that's a species with, it could be an atom, it could be usually it is an atom with unpaired electrons. And it's very reactive because its orbitals are unpaired and they're looking for electrons. So explain why NH2 is described as a free radical because explain why NH2 is described as a free radical because it's got unpaired electrons. That's why. By the amino free radical. So one of the orbitals of N, I mean, you can be very specific about this. N has, like N's electronic configuration, the outer shell electronic configuration is 2s2, 2px2, not 2, 2px1, 2py1, and 2pz1. So you can say that one of the orbitals of N is unpaired because it's bonded to 2 H atoms. So an H gives electrons to 2px and H gives electrons to 2py, but there's only 2 H's. One of the H, so one of the H is, one of the orbitals is unpaired. So you can be kind of very specific, I think, in this. अच्छा उसका मैं बता दूं कि free radical substitution gives a low yield. Why? Because when you have a free radical substitution, you don't get one product. You can get you can get multiple different products. Like if I have a ethane molecule and I want to do free radical substitution with it, what will happen is that that maybe this H, the Cl gets the H gets replaced by Cl, or maybe 2 of the hydrogens get replaced by Cl, or it could be all of the 6 hydrogens get replaced. So you're not getting one product. So if you're looking for one chloropropane, you're not going to get one chloropropane. You might get some molecules that would be one chloropropane, but they could be, I mean, any number of H could be substituted. So you're not going to get one product. You're going to get multiple products. So that's why you're going to have low yield because if you get 100 different products and the one that you're looking for is just one of them, so the percentage of what you're looking for is going to be less. Like if I'm looking for one chloropropane here, there's very little chance of actually one chloropropane forming. क्योंकि कभी कभार 2 हाइड्रोजन सब्स्टिट्यूट हो जाएंगे, कभी 6 हो जाएंगे, कभी 4 हो जाएंगे. So ठीक है, so I'll just reply after this. ठीक है, I'm just almost done. अच्छा, तो इसलिए remember, free radical substitution is a pretty bad reaction. It's because it can give you anything. It can pretty much give you so it's a very bad way of actually making halogenoalkanes, because you don't even know what halogenoalkane you're going to get. You pretty much know what halogen will substitute, but you don't know where it's going to get substituted. So बस ये आखिरी कर रहे हैं. Draw the structural form of the polymer made from this thing. Polymer from what? From this thing. They gave us acrylonitrile, this thing. So we need to figure out what is the polymer that's going to be made from this. So you got a double bond with 2 H's, and there's an H with a CN. So draw the structural formula of the polymer made from this. So the polymer that would be made would be this thing repeating over. The double bond would go away, linkages would form, and that's the polymer that's going to be formed. And this is an addition, polymerization. That's it. और उसके बाद vinyl alcohol cannot be polymerized in the same way because it will readily isomerize into another organic compound Z. Suggest the structural formula of the organic compound of Z. So this one, he's saying that CH2CHOH. So he is saying that this molecule readily, this molecule over here, it readily isomerizes into another organic compound. So we'll be basically looking for an isomer. So make an isomer of this. So it isomerizes into another organic compound. So I think that would be an aldehyde. Switch the double bond position and an isomer would be formed. The double bond at the moment is between the carbon atoms. Change the position of the double bond. Instead of being between the carbon atoms, you can put the double bond between the carbon and the oxygen atom. So the only isomer I can think of is this one. ठीक है, उस पर फिर 2 repeat units draw कर लो. The previous one, ठीक है, I kind of missed that part. ठीक है, it did show 2 repeat units. So make sure you just draw another one right next to it. I just suggest the structural formula of another isomer of vinyl alcohol which has cyclic ring structure. Of this one is vinyl alcohol. So a cyclic ring structure. So I can have the oxygen. And is it going to form an isomer? So cyclic ring structure. So this one, you have to, I think you should draw 2 repeat units. This is what you're going to draw. You're going to draw 2 repeat units. And the other thing is, you draw 2 repeat units. And the other thing is, make sure you show these continuation bonds. Don't put brackets around it. That's it. So that's how you're going to draw 2 repeat units without any brackets. But make sure these continuation bonds are shown. So cyclic ring structure, you had this thing. And he said that it isomerizes into some other compound. So I turned it into an aldehyde. And then he said that the same vinyl alcohol had a cyclic, it would isomerize into a cyclic ring structure. So I made this one. This one is also an isomer of this thing. And then he says, this molecule over here has been found in space. Give the structural formula of the organic formed when this thing. So all the reactions are for this thing over here. I've got Br2 in an inert solvent, so double bond. Br2 is going to react with it. So I think it's 3 carbon atoms. There's an aldehyde at the end. And H and 2 H's here. There used to be a double bond in the middle, but now that would be bromine. So that would be bromine. Then it's NaCN with dilute H2SO4. This is nucleophilic addition. This is this reaction. Where's nucleophilic addition? Nucleophilic substitution, nucleophilic. So this reaction over here. An aldehyde or a ketone, any carbonyl group would undergo this. They would end up forming cyanohydrin. Like you had a serial bond O, it would turn into a COH. And with a CN at the bottom. So you have an aldehyde, the CN -1 gets attracted. You need to know the mechanism of the reaction as well. You need to memorize this. CN -1 brings its lone pair, it's a nucleophile. It gets attracted to the positive carbon atom, bonds with it. The double bond electrons, because of the negative charge at the bottom, they get repelled to the top, where they then get attracted by H+1 and they form alcohol. So the double bond O turns into an OH with a CN. That's a cyanohydrin. नहीं, वो aldehyde को मैंने इसमें इस तरह बनाया था ना कि what I did was I had a double bond here between the carbon atoms. I just switched the position of the double bond. Instead of between the carbon atoms, I changed the double bond position. I put it between the carbon and the oxygen. So that's where I put the double bond. That's it. ठीक है नहीं I didn't change the position of the functional group in this case. I changed the functional group altogether. ठीक है, this was an alkene and an alcohol. I turned it into an aldehyde. ठीक है, exactly. So just remember, you can make a lot of isomers. Like if I can show you, I mean, for example, I mean, you should know that all you have to do is like if you have a carboxylic acid, like ethanoic acid, you can make a lot of isomers from it. All you have to do is remember there are three ways of making an isomer. You can either change the carbon chain. I mean, over here you can't really change the carbon chain because there's just two carbon atoms. But what you can do is you can change the functional group. You can change the position of the groups. Like OH is on this side. What I can do is I can change the OH and put it on the other side and keep the double bond over there. So that's like a functional group isomer. I've changed the functional group. What else can I do? I can change the double bond position as well. Like the double bond is between the carbon and oxygen. What I can do is I can put it between the carbon atoms. So that I can, so the oxygen would be single, so there must be an H with it. An H, and this would have just one OH. So what I did was I just changed the double bond position and put it over here. So I can do a lot of things. And then, so that's one thing. I can just keep on changing the position of the groups. I mean, I've got two OH over here, one OH over here, one OH over here. So I can have a molecule where I can have two OH on the same carbon atoms, and so on. So I can put the oxygen between the two carbon atoms. Like this oxygen is right at the on the left side. I can pick that up and put it between the two carbon atoms. So when you're making structural isomers, it's a free for all. You can do anything you like as long as the structure is correct and as long as the number of atoms are exactly the same. So you can change the carbon chain, you can change the functional group, you can change the position of the groups. So you can do pretty much anything. I said this one, we were on this, we had to do this carbonyl thing, a nucleophilic addition. So we were doing that. So NaCN would dilute H2SO4. The aldehyde will turn into, coming back to the question. So the aldehyde will turn into a cyanohydride. C double bond O, so it will turn into double bond O will turn into an OH. There would be a CN that would be attached to it and an H over here. So I've got an alcohol and I've got, I mean, this is a cyanohydrin. Then Toland's reagent. Remember this, remember the chart. I mean, where's the chart? Toland's reagent, that is specifically for, I mean, this one, aldehydes turning into carboxylic acid. So we got an aldehyde, it will turn into this side, the left side, sorry, the right side. You got an aldehyde, it will turn into, a carboxylic acid. And then you've got NaBH4. NaBH4 is a reducing agent. It will turn an aldehyde back into, again, the chart, aldehyde back into an alcohol. And it will by default turn into a primary alcohol. So turn the aldehyde back into an alcohol. So you had double bond, H and H. And this was the aldehyde, it will turn into an alcohol back again. That's it. So that's your reducing agent. So here, let's we'll try and do another session tomorrow at 10. Okay, everyone. Make sure if you need anything, notes, etc. So I've sent the number. या उसके ऊपर वेबसाइट के ऊपर मैसेज कर दो और ईमेल मी, ठीक है. I'll send किसको मैंने भेज देते. अच्छा, व्हाट्सएप अगर किया हुआ मैं भेज दूंगा, ठीक है. तो ज़हीब,
यस सर.
ठीक है, क्लियर है.
यस सर.